10.8 Taylor and Maclaurin series. The outline of this video is as follows. We will begin by introducing the core concept of A-series representation, which is a way to express a function as an infinite sum. From there, we will explore how to derive the specific coefficients required for a power series to match a given function. This will lead us to the formal definitions of Taylor and Maclaurin series, which are central to this topic. We will then see how finite versions of these series, known as Taylor polynomials, can be used to create powerful approximations of more complex functions. To solidify these ideas, we will work through several key examples, including finding the series for the functions 1 over x, e to the x, and cosine of x. We are now going to shift our perspective on power series. This change in viewpoint is the key to developing one of the most powerful tools in calculus. Previously, we started with a known power series and worked to identify the function it represents. We established that within its interval of convergence, a power series sums to a function that is continuous and has derivatives of all orders. This leads to a natural and important question: can we go in the other direction? If we begin with a function, f of x, that is infinitely differentiable on an interval, can we find a power series that is equal to that function? To investigate this, let us assume for a moment that such a series exists. That is, we assume f of x can be written as the sum, from n equals 0 to infinity, of some coefficients a sub n times the quantity x minus a to the power of n. The central problem we must now solve is this: if such a representation is possible, how can we determine the values of these coefficients? Here is the key insight for finding the series coefficients. We can isolate them by evaluating the function and its derivatives at the center point, x equals a. Let us start with the original power series for f of x. If we substitute x equals a, every term containing the quantity x minus a becomes 0. This leaves us with just the first term, so f of a is equal to a sub 0. Now consider the first derivative, f prime of x. When we evaluate this at x equals a, again, all terms with an x minus a factor disappear. We find that phi prime of a is simply equal to a sub 1. Moving to the second derivative, f double prime of x, evaluating at x equals a, leaves us with the constant term 2 times a sub 2. Rearranging this gives a sub 2 equals f double prime of a divided by 2 factorial. The pattern becomes clear with the third derivative. Atx equals a, we get f triple prime of a equals 2 times 3 times a sub 3, which is 3 factorial times a sub 3. Solving for the coefficient, a sub 3 is f triple prime of a divided by 3 factorial. Thus, each coefficient is determined by the corresponding derivative of the function evaluated at the center point. This process of repeated differentiation reveals a general formula for calculating any coefficient in a function's power series. By extending the pattern, we find that the nth derivative of the function f, when evaluated at the center point a, is equal to n factorial times the coefficient a sub n. Rearranging this expression gives us the formula for the coefficient itself. The nth coefficient, a sub n, must be equal to the nth derivative of f at a, all divided by n factorial. This is a powerful result. It means that if a function has a power series representation, that series is unique, and we now have a specific recipe to find its coefficients. Plugging this formula back into our original series gives us what is known as the Taylor series for f centered at a. It is f of a plus the first derivative at a times the quantity x minus a, plus the second derivative at a over 2 factorial times the quantity x minus a squared, and so on for all subsequent terms. This provides the required coefficients for constructing the unique power series that could represent a given function. This slide presents the formal definitions for the Taylor and Maclaurin series, which are power series constructed directly from a function's derivatives. The main idea is to use the value of a function and all its derivatives at a single point to build a corresponding power series. First, the Taylor series is generated by a function f at a center point, x equals a. The series is a sum of terms where the coefficient for the term, the quantity x minus a to the power of k, is given by a fraction. The numerator of that fraction is the kth derivative of f evaluated at a, and the denominator is k factorial. A Maclaurin series is a very common and useful special case of a Taylor series, where the center point a is chosen to be 0. For a Maclaurin series, all the derivatives are evaluated at x equals 0, and the terms are powers of x instead of powers of x minus a. In short, the Taylor series is a power series built from a function's derivatives at a chosen center point. To build the Taylor series for the function 1 over x centered at a equals 2, we must first calculate the series coefficients. This process involves repeatedly taking derivatives of the function and then evaluating them at the center point. Let us start by finding the first few derivatives of f of x equals x to the power of negative 1. The first derivative is negative x to the power of negative 2. The second derivative is positive 2 factorial times x to the power of negative 3. We can see a pattern emerging. The general formula for the nth derivative is negative 1 to the power of n times n factorial times x to the power of the quantity negative n plus 1. Next, we evaluate each of these derivatives at our center, a equals 2. This gives us the sequence of values shown on the right. The final step is to find the Taylor coefficients, which we call a sub n. The coefficient a sub n is the nth derivative evaluated at 2, all divided by n factorial. When we perform this division, the n factorial term cancels out, leaving a simple expression for our coefficients. Negative 1 to the power of n, all divided by 2, to the power of n plus 1. Plugging these coefficients into the power series formula gives us the Taylor series for 1 over x, as shown at the bottom of the slide. Now, let us analyze the Taylor series we just generated for the function f of x equals 1 over x. We will show that this series actually converges back to the original function, but only within a specific range of x values. The key insight is to recognize that this is a geometric series. A geometric series is one where each term is the previous term multiplied by a constant factor. In this case, the first term, which we can call a, is 1/2. The common ratio, r, is the negative of the quantity x minus 2, all divided by 2. We know that a geometric series converges only when the absolute value of its ratio r is less than 1. Applying this condition, we find that the absolute value of x minus 2 must be less than 2. This inequality tells us that the series converges for all x in the open interval from 0 to 4. Finally, we can use the well-known formula for the sum of a convergent geometric series, which is a divided by the quantity 1 minus r. Plugging in our values and simplifying the algebra, as shown on the slide, reveals that the sum is exactly 1 over x. Therefore, the Taylor series for 1 over x centered at 2 is identical to the function itself, but only on the interval from 0 to 4. We are now ready to generalize the concept of linear approximation to create more accurate polynomial approximations for a function. This leads us to the formal definition of a Taylor polynomial. For a function f with at least n derivatives at a point x equals a, the Taylor polynomial of order n, written p sub n of x, is constructed using the function's derivatives at that point. As you can see in the formula, Each term consists of a derivative of f at a divided by a factorial and multiplied by a power of the quantity, x minus a. You have already seen the simplest case. The Taylor polynomial of order 1 is just the linearization of the function at x equals a. We use the term order n instead of degree n because the coefficient of the highest power term, which depends on the nth derivative, could be 0. The essential idea is that Taylor polynomials provide the best possible polynomial approximation of a given order to a function near a specific point. Let us now derive the Maclaurin series for one of the most important functions in calculus, the exponential function. F of x equals e to the power of x. The process starts by taking successive derivatives of the function. What makes the exponential function so special is that its derivative is always itself. This means the first derivative, the second derivative, and in fact every derivative is simply e to the power of x. Next, we evaluate these derivatives at the center of the series, which for a Maclaurin series is x equals 0. Since e to the power of 0 is 1, every single derivative evaluated at 0 is equal to the number 1. This makes the coefficients for our series remarkably simple. The coefficient a sub n is the nth derivative at 0, which is 1, divided by n factorials. Plugging these coefficients into the series formula gives us the sum from k equals 0 to infinity of the quantity x to the power of k over k factorial. The Taylor polynomial of order n is the sum of these terms up to the nth power. This slide presents figure 10.17, which gives us a visual understanding of how Taylor polynomials approximate a function. The main curve shown is the graph of the function f of x equals e to the power of x. We are building these polynomial approximations centered at x equals 0. Spread. The first-order polynomial, p sub 1 of x, is the familiar tangent line to the curve at that point. It serves as the best linear approximations. The second-order polynomial, p sub 2 of x, is a parabola. Notice how it hugs the curve of e to the x more closely and over a wider interval than the tangent line does. Finally, the third-order polynomial, p sub 3 of x, is a cubic curve that provides an even better fit. The key takeaway is that as we increase the order of the polynomial, our approximation becomes increasingly accurate, especially in the neighborhood of the expansion point. Now let us apply the same process to find the Maclaurin series for the cosine function. This requires us to find the values of the function and all its derivatives at x equals 0. First, we list the derivatives. The function itself, cosine of x, is 1 at x equals 0. The first derivative is negative sine of x, which is 0. The second derivative is negative cosine of x, which is negative 1. The third derivative is sine of x, which is 0 again. A clear pattern emerges, where the values of the derivatives at 0 cycle through the sequence 1, 0, negative 1, 0, and then repeat. This means that all the odd-numbered derivatives are 0. Consequently, all terms in the series with odd powers of x will have a coefficient of 0 and will vanish. The resulting series contains only even powers of x, with alternating signs. This gives us the final Maclaurin series for the cosine of x. This slide presents a figure that visualizes the Taylor polynomials for the cosine function we just derived. The main purpose here is to see how the quality of our approximation improves as we include more terms in the series. The central, oscillating curve is the actual graph of y equals cols of x. The other curves are the Taylor polynomials of increasing even order, from p0 up to p18. Remember that for the cosine series, the polynomials of order 2n and 2n plus 1 are identical. As you can clearly see, the lower-order polynomials are only accurate very near the center, x equals 0. But as we increase the order n, the polynomial graph hugs the true cosine curve over a wider and wider range. By the time we get to the polynomial p18, the approximation is visually identical to the cosine function over a large interval. This graph provides strong visual evidence that the Taylor series for cosine converges to the function itself. Now let us look at a fascinating and important counterexample. While Taylor series are incredibly powerful, it is not always guaranteed that a series will converge back to the function that generated it. This slide shows a classic case where this representation fails. Consider the piecewise function shown here. It is defined as e to the power of -1 over x squared for all non-zero x, and it is defined to be 0 right at x equals 0. Although it is not obvious, it can be proven that every single derivative of this function, when evaluated at x equals 0, is exactly 0. Think about what this means for its Maclaurin series. The coefficients, a sub n, are calculated from the nth derivative at 0. Since the numerator is always 0, every single coefficient in the series is 0. This means the resulting Maclaurin series is simply 0. The series converges for all x, but it only equals our original function f of x at the single point x equals 0. This example proves that just because a function's Taylor series converges, it does not necessarily converge to the function itself. This slide presents figure 10.19, which provides a crucial counterexample to an assumption we might be tempted to make about Taylor series. The function shown is y equals e to the power of the quantity -1 over x squared, which we define to be 0 at the origin to make it continuous. What is so special about this function? It is incredibly flat at x equals 0. In fact, it can be proven that not only is the function's value 0 at the origin, but every single one of its derivatives is also 0 at that point. Now recall that the coefficients of a Taylor series are built from these derivatives. Since all derivatives are 0 at x equals 0, every term in this function's Maclaurin series is 0. This means the Taylor series is just the constant function 0. As you can see from the graph, this series only matches the original function at the single point x equals 0. This example proves that an infinitely differentiable function's Taylor series does not always converge to the function itself. The examples we have just discussed highlight a critical uncertainty. Just because we can generate a Taylor series for a function, and that series converges, it does not automatically mean it converges to the original function. This reality forces us to ask two very important questions. First, for what values of x can we be sure that a Taylor series actually converges to the function that created it? Second, if we use a finite Taylor polynomial to approximate the function, how accurate is that approximation? In other words, how can we quantify the error? Answering these questions is essential for using Taylor series reliably. Fortunately, a powerful result known as Taylor's theorem provides the framework to answer both of them. And that is what we will investigate next. Let us summarize the essential concepts of this topic. We started with the foundational idea that if a function has a power series representation centered at x equals a, then that series must be its Taylor series. This uniqueness allowed us to derive a precise formula for the coefficients. A sub n is equal to the nth derivative of f evaluated at a, all divided by n factorial. We then defined the Maclaurin series as simply a special case of the Taylor series, where the center point A is 0. Practically, we use finite sums of these series, called Taylor polynomials, to create powerful approximations for the function, especially near the center point. However, and this is a critical point, a function's Taylor series might converge to something other than the function itself. We cannot assume they are equal without verification. The main takeaway is that Taylor series give us a systematic way to build a series for a function. But convergence to that function must always be confirmed. To wrap up this lesson, let us review the main ideas with two questions that will help check your understandings. First, a practice calculation. Find the first four non-zero terms of the Maclaurin series for the function f of x equals sine of x. The procedure for this will be very similar to the one we followed for the cosine function, but you will find that a different set of terms remains. Second, a more conceptual question. Explain why the Maclaurin series for the special function from example 4 is not useful for approximating the function away from the origin. Recall that this function was f of x equals e to the power of the quantity -1 over x squared, and all of its derivatives at x equals 0 were 0. Take a few minutes to work through these problems. Answering them will help solidify your understanding of how to build a Maclaurin series and when that series is a useful representation of the original function.